Hello, my name is Lily Alterman, and today I will be presenting to you Lab 5, all about the falling Slinky. Now, the purpose of this lab is to examine the motion of a Slinky system where the Slinky is starting at a man's head and is dropped from that height. And from this, we're going to determine whether the bottom of the Slinky stays stationary or it moves. Now, for introduction, Newton's second law, which is also known as the momentum principle, relates the total interactions to the changes of motion in the system and can be seen by this formula here on the left. And then also, just as a little note, the force of gravity is only going to be impacting our system in the y direction, and that is going to be a negative mg in our vector. Now, the force of drag is the direction opposite of the object's direction of motion, and then the magnitude is proportional to the square of the object's speed, which is the turbulent drag, and can be seen from the formula below. And then Newton's second law also gives us the velocity and position update formula, which will be useful for modeling our motion later. And then the terminal velocity is when drag equals gravity and the net force equals 0, and thus there is no acceleration. And this might be useful depending on what speeds we get in this lab, but we will probably not be using that today. Now, also, our modeling programs we use. We're going to be using WebPython and Tracker today. And just as a note, the height of Derek, the man holding the Slinky right here in the right, it has been estimated to the best of my abilities. While I'm not as good as the man on TikTok who could tell anyone's height, I did try my best. Now, our assumptions. I'm assuming that there's no work from the surroundings of the system, like there's no wind, there's no external forces, nothing. And the force of tension also equals the Slinky force. And then I also assume the force of the Slinky and the force of gravity cancel out. And then our system is the man holding the Slinky, and the ground itself. And we're saying the force of gravity equals negative mg, thus the force of the Slinky is going to equal mg to cancel out, as you can see in this little force diagram to the right, kind of depicting that. Now, the tracker simulation. We had our mass as 0.218 kilograms, our starting height of 1.75 meters, our initial velocity is 0, our initial position is a little bit off because of where I ended up putting my axis when I was defining them over here, but otherwise that is what we have. And then if we run this, you can see the simulation going, and it drops, and we can even just see in the simulation that bottom is definitely staying there for a while. Now, next, we have our WebPython simulation. So this is just all our initial conditions that we already declared before. We already said what all these were: the mass, the velocity, the starting position, our delta t, our gravity, and then our drag, which did end up being 75. Now our motion prediction and simulation loop is right over here. We used our time constant of while it's less than 0.7, which is the time it was falling and then hit the ground in our video. And then we just have our formulas here. This is our F net we calculated by setting and finding the force of the gravity, setting that equal to the negative of the force of tension, and then we found all our values there. So as you can see, this is our WebPython simulation. Let's see, I run it right here, and then it's just a complete straight line for that position, which is what we wanted for the bottom. Now our results. We did get, for our experimental data model, it is pretty much consistent and a consistent height all the way until the end when it drops off, and that is just the whole thing itself falling. It eventually catches up to itself and falls, which is to be expected, but this part right here is practically a straight line and was what can be expected, and then the computational data model gave us a straight line because it is indeed all computational and there was no external effects that we could have simulated with. And then for our possible errors, human inaccuracies with the tracker position placement. I did try my best, but my eyesight is not perfect, so some of the positions can be placed off, giving us the not perfectly straight line right here. And there were no more forces that we took into account. For example, like there could have been a wind blowing that day that we didn't take into account, which would have been another force in the system, accounting for the not completely straight line. And now the what if and what does questions. What does it mean? So basically, did my Slinky not move? Did it stay stationary? And yes, it stays stationary, but why does this happen? It happens because the forces in the y direction cancel out, and then the Slinky acts like a spring and then cancels out the downward gravitational force with an equal and opposite tension force. And what if let's say we had a larger weight at the bottom of the slinky, would it still remain stationary at the bottom? And this very much depends on the situation. As long as the slinky is large enough that the force of the slinky and the force of the tension counteracts the force of the gravity, then it would remain stationary. And then here is my citations and Python link. Thank you so much and have a lovely day.